we have an assignment due. There will be one more assignment on the topic of the simple harmonic oscillator, which will be distributed later on. And then we will have an exam. The exam will cover the material through the simple harmonic oscillator, which we might finish today. We might finish tomorrow. I mean, well, probably won't finish it tomorrow, but we could finish it on Thursday. And then we will have an exam. Well, I haven't quite decided about the exam. I wanted to get your opinion. So, question is, what would you prefer? Would you prefer an exam of the type of the first exam, or would you prefer a tape?
Wait, will the difficulty be different?
Yeah, absolutely.
What the tape will be like?
Well,
But you're just going to design to be like horrendous, right?
no, horrendous.
Yeah.
I'm this kind of guy. Maybe. No, the idea would be that there would be a lot less time pressure. The take-home exam, the idea is not to be, of the difficulty scale of a homework assignment, but something that you have more time, but will be, a little bit more involved, But that has pluses and minuses, obviously, right? So think about it, and you can send me an email with your feedback, and we'll decide.
You can just do one of those polls again.
I'll just get your feedback, so let me know. Alrighty. Right. So we're talking about the simple harmonic oscillator. In the last lecture, we were talking about different representations of the quantum problem with respect to different bases. Okay. So we could express our representation in terms of what are called the number states, which is a countably infinite set of vectors that span the Hilbert space. The number states are the eigenstates of a dagger A. They are the eigenstates of the number operator. And of course, they're also the energy eigenstates, right? And they form a resolution of the identity. Alternatively, we could look at representations with respect to the span of the states that are eigenstates of the position and momentum operator. Okay, those eigenvalues are continuously infinite, but nonetheless they form a basis for the space. They form another resolution of the identity. And we, of course, look at position and momentum representations. Those are the wave functions, right? So we could talk about the state in terms of its expansion in the number basis or its expansion in terms of position and momentum states, okay? So we have different representations of operators. The raising and lowering operators with respect to the number basis are matrices. They're infinite dimensional matrices, but matrices nonetheless. Same for position and momentum. In the basis and the representation of position and momentum, of course, then position and momentum operators have representations as multiplication by constants and derivatives. Those operators then are the wave mechanical operators that one is typically introduced to in introductory quantum mechanics. Yeah?
I thought P was C dagger minus A.
You are correct. No, hold on, let me think about that for a moment.
You had it right.
No, that's no, it is correct, that's a step. It's in my-
Is it because of the I?
No, the I's in the denominator.
Oh.
That's correct. Yep, that's correct. The reason we know that is that, of course, A is x plus I and D. Right? So you subtract from A dagger, you divide by I, and you get the right thing. All right. The energy eigenfunctions, that's to say the positional momentum representations of the energy eigenstates, are easily derivable by just saying, by this defining equation. The ground state is annihilated by the lowering operator. So when we look in the position representation, we have a differential equation for the ground state wave function, which we can solve. And that equation tells us that the ground state of the simple harmonic oscillator is a Gaussian. And the higher energy levels, the excited states, are obtained by applying the creation operator to that. And the creation operator applied to that involves taking the dagger of this, which is x minus the derivative with respect to x, n times on this. And what we get are these functions. Those functions are Gaussians that are multiplied by Hermite polynomials. The Hermite polynomials can be written in this way, compactly. In fact, there are a number of properties in sort of traditional theories of special function differential equations and so forth. We used to study this kind of thing ad nauseum. We don't so much anymore. But one of the things that's, for example, a useful property of Hermite polynomials, which is a kind of property you see of all hypergeometric functions, is so-called generating function. The generating function tells us a way of obtaining the Hermite polynomials from a power series. So if I look at, as a function of some parameter t, that Gaussian, one can show fairly easily that this is equal to the following. So the Hermite polynomials are the expansion coefficients in a Taylor series expansion. There's an intimate relationship, which is basically due to this factor between Gaussians and Hermite polynomials. The other thing that we mentioned, briefly, it's very easy to see, is that the wave functions that are associated with the energy eigenstates in position space are exactly the same as they are in momentum space. And that's not surprising because the Hamiltonian is completely symmetric in position and momentum, right? And it's just a question of a phase convention that we have. So in momentum space, the energy eigenfunctions are exactly the same with a factor, just to keep everything self-consistent, of I out front. Okay. course, we know that because we have a reflection symmetric potential for the simple harmonic oscillator about the origin, the eigenstates of the Hamiltonian are symmetric and antisymmetric functions. So this is the ground state written which has a 0-point energy, and then we have the first excited state, the second excited state, etc. All right. So let's continue a little bit further along this path. One thing we didn't discuss that I wanted to get to last time, but we didn't get it far, is to ask the question about the uncertainty in positional momentum. So let's look at the energy eigenstates. The number of eigenstates, of course, are not eigenstates of positional momentum. They're wave functions that are distributed in space and momentum space. So they have a finite extent, right, and therefore a finite uncertainty. Now, just looking at this equation, or equivalently momentum space, you should be able to read off what the uncertainty is of the ground state.
Get H bar over 2.
Sorry?
H bar over 2.
Well, there's some H bars there, I mean, that's not quite the units of X or P, those are units of the action.
Oh, I'm turning it off.
So what I'm asking is the following question. We have, in position space, we have this expression for this. So what that tells me, of course, is that the probability distribution in position is the square of the wave function, right? The probability density, which is 1 over the square root of this, e to the minus x squared, right? Now, is that a normalized function? Absolutely. It's a Gaussian, and everyone remembers by heart the form of a normalized Gaussian. And if you don't, you will memorize it now. Okay? And what is the form? If I have a Gaussian with RMS with sigma and mean x bar, what is the form of the Gaussian distribution in X?
Quantity x minus x vector of x quantity squared over 2 sigma squared.
2 sigma squared. And this goes like
1 over square root of 2 times sigma squared.
yeah, everyone's going to put that in there, right? Okay? Used to be on the Deutsch mark before the euro. So I used to carry it around. Gauss's picture on it. It was very useful. Okay, so with this, what is the mean value of position for the ground state? 0. And what is the uncertainty? Of course, the uncertainty here, or sigma, right? 2. Voila. So in the ground state, this is x squared. We have these relations, okay? Or I should say the RMS with the uncertainty itself in dimensionless units is 1 over square root of 2. Okay, so you can read that off. What about a momentum? It's the same, because they're the same wave function. So in dimensionless units, we got this. What about in dimension full units? What is the uncertainty in position? How do I put the units back?
We just multiply by that xc.
X, absolutely, thank you, Paul. We have a characteristic, so everything is in units of the characteristic scale, so we multiply that by xc. And then we have to look back and see what the heck xc was, and that was the square root of h bar over m omega. Okay, so that's the uncertainty in position of the ground state and position units. We call it delta x 0, just to emphasize that this is for the ground state. Okay? And the uncertainty in momentum space is the characteristic momentum, which is equal to square root of h bar times m omega. So we have h bar m omega. So the characteristic scale that we derive just from numerology, basically, dimension analysis, are essentially, up to these factors of 2, the widths of the wave function of the ground state. Okay. And we know that generally that the product of the uncertainties must satisfy the Heisenberg uncertainty principle, right? And what is this in this case? This product. H bar over 2. So the ground state of the harmonic oscillator is a minimum uncertainty wave factor.
That's because it's Gaussian?
It is true that the only minimum uncertainty wave function is a Gaussian, but it is not true that every Gaussian is a minimum uncertainty wave packet. As we will see in homework next time. But in this, for the ground state of the harmonic oscillator is a minimum uncertainty wave packet. Okay. Now, what about the higher excited states? What is the uncertainty in position momentum for them? Well, that's a more tedious thing to do in wave mechanics. I mean, you could do it with the Hermite polynomials and the generating functions and integrals, but it's trivial to do it in the number representation. So that's how you should do it. Okay? So let's do it. So what I seek is the mean position and momentum and the uncertainty. For the energy level. That's what I see. Okay? And the way to calculate that most easily is to use the algebra of A and A dagger. Okay? So let's do it. Of course, x is A plus A dagger over root 2, and p is A minus A dagger over I root 2. Okay. So, first of all, just quickly, what is this?
0.
0. Right? There is no mean value of A or A dagger for a number state because this raises or lowers, right? So what that tells me is that for a position eigenstate, for a number eigenstate, there is no mean position. Of course, we could have read that off the picture. It's a symmetric potential, and the eigenfunctions squared are all symmetric functions. So therefore, the mean position is always 0 in a parity symmetric potential. So that's got to be true. All right, what about the uncertainties? Well, that tells me that the uncertainty in position is equal to the expected value of the square, since the mean itself is 0, right? And that is equal to A plus A dagger over root 2 to the power n.
Power 2.
Sorry, to the power 2, thank you. Otherwise that would be hard. Okay, so now here's another trick of the tricky. Whenever you're dealing with looking at the algebra of A and A dagger, and you want to calculate something like an expectation value, the only non-zero terms are the ones that have an equal number of power of A's and A daggers, right? So I'm looking at the expected values back at n. Because otherwise, on one side I'm raising more than I'm lowering. Yeah?
But that only applies if n is not equal to 0. If n is equal to 0, then you can only have that A dagger term.
True, but it's not that it doesn't negate what I said. The only terms that are certainly not 0 are those. Then in addition, there would be additional ones that are 0. So that means that, generally speaking, the only terms that survive are the ones with the equal numbers of A's and daggers. So there's an A dagger, and there's an A dagger A. Now, as Stephen pointed out, if this were the ground state, then this term would not be there. All the terms that are so-called normally ordered, where the A's are on the left, and the A's are on the right, and the A dagger on the left vanish. But this is general. Okay? So how do you deal with this? Well, the easiest thing, again, is to, what we say is normally order this. Put this in the form where A daggers are on the left and the A's are on the right. That's just a jargon. It comes to there, it's just called normal order, but don't worry about that. Why? Because then this is the number operator and we know how it acts on A. So this is equal to A dagger A plus the commutator of A and A dagger. Right? Which is 1. So this is equal to 1/2 this A dagger A is the number operator plus 1 times n. So the expected value of x squared is that, which is n plus a half. And it's very easy to show in exactly the same way that the expected value of p is the same thing as it should be, because it's got to be symmetric in x and p for the eigenstates of the Hamiltonian, because the Hamiltonian is symmetric in x and p. Okay. What this says, of course, is that the energy is equally distributed between the kinetic energy and the potential energy, right? The Hamiltonian in dimensionless units is a half x squared plus p squared. And we know that this is n plus a half. So it's not surprising, we didn't even have to go through that, this thing, we could have just read that off by fiat as well. Alrighty, so what this tells me is that the uncertainty in position is square root of n plus a half times the square root of h bar over omega and p sub n good. So are these minimum uncertainty wave packets? No, right? The product of these uncertainties, this is, I'm sorry, of course, with the dimensions back in, so give a little lowercase letters. Only for the ground state is this a minimum uncertainty state. All right, very good. So let's talk now about dynamics. So our central player in talking about dynamics is the time evolution operator. Okay. Time evolution operator is e to the minus I over h bar ht. Right? And the Hamiltonian I can express in terms of x and p or in terms of A dagger A. So if I put in the Hamiltonian, this becomes e to the minus I omega A dagger A plus a half times time, omega t. Right? It's the time evolution operator. Or, right, factor out this e to the minus I omega t times the number, e to the minus I, the number operator times omega t. Now the 0 point energy is there, but as I've emphasized in the past, the absolute value, or what the value of the ground state energy is irrelevant to dynamics. The only thing that affects the dynamical evolution of the system is the relative energies, okay? So typically we ignore this in talking about dynamics. You can put it in there, but it's an overall phase factor that doesn't affect any prediction of any probability, because it's never going to affect the relative phase of anything. Okay? So we can completely ignore it. Just, you know, it's just where we decide to put the zero of energy. All right, so if we wanted to look at time evolution, there's lots of ways we could do it. Let's talk about the Heisenberg picture. And again, there's lots of ways we could think about the Heisenberg. Let's look at the Heisenberg equations of motion, first of all. So, let's look at the and what is that in this case? Well, if I write out what that is, I have h is there, I have minus omega, I have minus I omega over 2 times the commutator of and what is that commutator? Well, x commutes with x squared,
Isn't it just
and x with p squared.
the 2 cancels it out?
Right? So this becomes 2i p. Remember that the commutator of x and p in dimensionless units is I. So this is equal to omega p. And similarly, the time derivative of momentum is minus omega x. If I wanted to just write, and there's lots of many different ways to do the same thing. The time derivative of A minus I omega, the commutator of A with H, that's equal to minus I omega, the commutator of A with A dagger A, which is equal to minus I omega A. So I get d by dt of A is minus I omega A. So what we see here is that the Heisenberg equations of motion for the harmonic oscillator are exactly the equations of motion that we had for the classical canonical chords. Exactly. There's nothing different about them. Right? And we can write down the solution. The Heisenberg operator A, W of t, is A0 e to the minus I omega t. And x of t, the solution, we can get that by writing A plus A dagger over root 2. Is x is 0 cos omega t plus p is 0 sine omega t, and p of t minus A dagger over I root 2 is P0 cos omega t minus X0 sine omega t. So, that's a very important result. It says the harmonic oscillator has, in some sense, looks entirely classical. Yeah.
This looks like it's relevant in what we were supposed to be doing for like the squeeze operator in Homer, because the format just seems too similar to be.
They're similar, but I mean, indeed there is the squeezing operator isn't related to this kind of operation. It's something different, but the mathematics is quite similar. In fact, I would say another way of getting this solution, instead of solving the differential equation, is just to directly time evolve the operator according to the unitary transformation, right? That's another way we can get exactly this. Using the Baker-Campbell-Hausdorff, this is equal to e to the plus I n hat omega t, A0, e to the minus I n hat omega t. And then use multiple commutators. This is equal to the sum n equals 0 to infinity. The multiple commutators n times. Right? So there's many ways we can get the same thing. All right, so what we see here is that for the simple harmonic oscillator, the expected values follow the classical trajectories. That's an important result. That's unique to the harmonic oscillator and a free particle and a linear potential. If something is no more than quadratic, then that is the case. So what we have here is that the average x follow the classical trajectories. Now, that brings us to a very interesting topic that we're going to spend the rest of our time on the harmonic oscillator, asking about the question of the classical limit. What is it? What do we mean by the classical limit? In what ways can we think about the quantum simple harmonic oscillator like a classical simple harmonic oscillator? You remember last lecture, we were talking about the correspondence principle, right? We talked about the idea that when we go to very high quantum numbers, high energies, where the Broglie wavelength was very small compared to the scale over which the potential changed, that there were aspects of the classical trajectory encoded in the energy eigenfunctions, according to the WKB approximation, right? So we said, come back, come over here, we have the correspondence. So let's talk a little bit about that. So if I have my simple harmonic oscillator, and I have some highly excited state, then the wave function is such that it's very peaked near the classical turning points, which is kind of what you expect for a harmonic oscillator. If I ask what's the probability to find the position of the harmonic oscillator somewhere, it spends most of its time near the turning points and little time where the kinetic energy is large, right? And so the amplitude of this, on average, looks like the classical, we had the wave function associated with this state was proportional to 1 over the square root of the classical kinetic energy at that position, where the classical kinetic energy at that position is, I mean, the classical momentum is the square root of the kinetic energy, which is the total energy minus potential times 2m. So, in some sense, there's an aspect of this which contains the classical dynamics in it. But if I prepared the harmonic oscillator, the quantum harmonic oscillator, in this wave function, if I somehow were able to create this energy eigenstate, would you say that the predictions of measurements that you would do would be what you would expect classically? Classically, this thing oscillates, right? And classically, the position of this guy, or I would just say this, classically, right? What about if I prepared the state of the system in this state? What does this do? Does it oscillate? What is the expected value of position as a function of time? Does it oscillate?
Still 0.
It's 0. Why? Well, it's true that the Heisenberg operators follow the classical trajectories, but for this guy, the mean value is 0 at time equals 0 for both of these things. And so it's 0 for all times. This is a stationary state. And for a stationary state, nothing, no probability of anything changes as a function of time. So stationary states are not associated with classical trajectories. You need to have a wave packet of different energy eigenvalues in order to have anything change as a function of time. Okay. Stated another way. So let me first state it this way. So stationary states are stationary. Nothing changes with respect to time. So stated another way, if I look in phase space, well, the states of definite energy lie on the circle. Okay? Let's put it in the units. Sorry, so this is alpha as a function of time. And this thing has a definite energy. Characteristic energy times alpha squared. A stationary state is a state that corresponds to something which is completely uncertain where I am on this circle. I'm on the circle, but my position momentum is not here or here or here, it's anywhere on this. So if I had a classical probability distribution on phase space, suppose that I prepared my harmonic oscillator, but I didn't tell you what little kick in position I'm going to give to you. And you had to, you just then would assign a probability distribution. I said it's going to have this energy, but I'm not going to tell you what its initial position and momentum are. Well, then you would say, well, it's on this circle, but I don't know where. Okay? That's a classical hidden variable, missing information. You assign a probability distribution based on your lack of knowledge about that. In which case, as a function of time, well, the position momentum would be the same probability distribution, because this whole thing is rotationally symmetric. And so that probability distribution would not change as a function of time, because every point on this curve moves around with angular velocity omega, and they all stay the same. Okay? So that's the classical analog of the quantum stationary state. Okay? So if we want to define a something that looks more like a classically oscillating particle whose position and momentum oscillate with time, we cannot look at a single stationary state. We need to think about a wave packet, which is a superposition of energy eigenstates. In fact, we see that already here in this classical phase space. What we have here is that if I have an energy, a state that has a definite energy, it has a completely uncertain phase. Let's just say the classical trajectory is one where this phasor, the phase of this oscillator changes as a function of time. Right? So what we see here is that from the quantum mechanical point of view, so let me summarize a few things. To quantumly, to see dynamical change in the mean x and p, we need to consider a wave packet superposition of energies. Now, the relationship to this notion of phase is the following. We see the time evolution operator generates rotations in phase space. Right? So this phasor is rotating at an angular velocity omega. So that means that the number operator is the generator of displacements in phase. In the same way that we said momentum was the generator of displacements in position, and position was the generator of displacements in momentum. The number, which is related to the magnitude, is the generator of displacements in phase. In fact, this comes back to another point that's written here. We had two different ways of expressing this complex amplitude. We can express them in terms of the real and imaginary parts, which were the quadratures, which are the position and momentum. And those, we said, satisfied, when we quantized them, they were the canonical operators and they didn't commute. What about the polar representation? I mean, I can look at this for different energies and there are different coordinates here. I can look at this in polar coordinates, right? Can I write down a polar representation of the So quantumly, the classical amplitude, complex amplitude, becomes the annihilation operator. So we had alpha of t became A of t. Let me just say alpha at any time. X plus I or X and t. Don't commute. But what about that representation? We know alpha is this magnitude times the phase. Can we write the annihilation operator in a polar decomposition? Remember the polar decomposition? That horrible problem in the first week of no one knew what the heck is he making us do this for? Here's the way. So you remember we showed in homework that we should be able to express an operator. It might be natural to think, okay, there is a unitary and then the square root. Right? That was the polar decomposition. This is a unitary. This is A, and this is A over A. This has the form of e to the I phi hat, where phi is the remission operator, times the number operator, which is what you might have guessed. Right? the amplitude is the square root of the number, the magnitude of the amplitude, and then there's a phase. Now, there's a problem with this. What's the problem? Well, in fact, I'm going to put the hat over the whole thing for a reason you'll see why in a moment, not over that. Let's look at what this operator is. We know that this operator in the number basis is the square root of n minus 1, n 1 to infinity, right? This operator is, what is this operator in the number basis?
Just diagonal.
It's diagonal with eigenvalues,
N increasing.
square root of n, right? That's what this is, right? So it's invertible. 1 over that is 1 over the square root. So I can just take the inverse of that. So this tells me that this operator, this thing that was the unitary in the polar decomposition, is equal to n equals 1 to infinity. So I'll write it over here. E to the I, that big hat on it. Okay. It looks kind of unitary because unitary operators take bases to bases. But there's a problem. Let's look at the product of this with its adjunct. If this were a unitary, this should be the identity operator, right? U times U dagger should be 1. What is it equal to? Well, I have the sum n equals 1 to infinity, n minus 1, n, and then the adjoint. All right, but the problem with that, oh, no.
Yeah, that one.
No, that's, okay, this one's fine,
Yeah.
right? This is n equals 1. Which is also equivalent to n equals 0 to infinity and to infinity, which is the identity. That's cool. There's no problem with that. However, if I look at this, I get this, which is equal to 1 minus the projector on the ground state, which tells me that these two operators don't commute. Therefore, it's not a normal operator. It's not unitary, because of this fact that I can't lower beyond 0. Okay? So what that means is that this polar decomposition is kind of bogus. It only holds always for finite dimensions. But for infinite dimensions, I can't exactly do this. I can write it this way. I mean, this is true. This is correct. But it's not unitary. which means if it's not unitary, there exists no Hermitian operator that I call the phase operator. There is no Hermitian observable. Corresponding to phase of the oscillator. Now there's been umpteen papers written about this and what this means, how to interpret this. But I can say a few things that are important. This doesn't mean that we can't still talk about the measurements of the phase and the fact that in some sense, number and phase of the oscillator are conjugate variables. In the same way that position and momentum are conjugate. So, if I come back over here, what we said is that if I had a state that had a definite energy, it has a completely uncertain phase. If I want to make something that has a definite phase, it's going to have an uncertain energy. Phase and number are conjugate in the same way that position and momentum are conjugate. Let's derive that and explain what we mean. So if I look at the commutator of this operator, okay, so that's equal to n minus 1 minus n. Right? Plugging in our value for that, which is equal to minus, let's of course learn the whole thing. So what that says is that in some sense, the number operator looks like the generator of phase translations, which is equal to I d by d phi. Okay. Or equivalently, phi hat is kind of like the derivative with respect to n. In the same way that position operator looks like the derivative with respect to momentum in the momentum representation, and momentum looks like the derivative of position in the position representation. Now, why isn't this exactly true? Well, it comes back to this picture. You see, I can translate in x and p arbitrarily, but it's the fact that there's this singularity here, this origin. I can't go below n equals 0. If it was really just a derivative, I should be able to go through to the other side. But I can't. And that's the mathematical problem. Nonetheless, what this tells me is that in some sense, as long as I'm not near that singular point, that this is approximately as long as I'm not really close to that singular point. And what that tells me is that there is a kind of number phase uncertainty relation. if I want to create a quantum state that has a well-defined phase, it must have an uncertain number, an uncertain entity. It must be a wave packet consisting of many different number states. It's the only way I can do it. The state that has a definite number has a completely uncertain phase. What about states with definite phase? Well, I can define the following. Let's define phase states. To be an equal superposition of all the number states. This is analogous to the fact that a position eigenvector is a superposition of all momentum eigenvectors, and momentum eigenvectors are equal superpositions, right? Why is it fair to call this thing a phase state? I said there was no phase operator. There is no Hermitian operator that I can consider to be the phase which I could measure. But we do have this operator. Let's see how this operator acts on this state. Now I can rewrite that which is equal to e to the I phi times that state plus the vacuum. So this state, as long as I don't have much of the vacuum, I'm not close to vacuum, this state looks kind of like an eigenstate of that. If it were a unitary, then we know the eigenvalues would be phases. But it's not quite a unitary. It's got this extra thing that happens near the origin. Nonetheless, this is a set which spans the space and can be considered to be, you can show, nonetheless, if I integrate over all these phases, I get a resolution of the interval.
That can't be just phi.
Oh, I'm sorry. Yes, thank you. I changed. Pardon me. So, are these, if we have this resolution of the identity, can't we make a Hermitian operator just out of, I mean, why don't I just define it's diagonal in that representation. Well, the problem is that these guys are not orthogonal kets. It's not Hermitian because these guys aren't orthogonal. This times this is not this. Nonetheless, we have a way of thinking about phase because we have this relationship. What this is telling us is that we have a resolution of the identity in terms of positive operators. This is what we discussed during the semester as a POVM. Which is to say that we have a probability distribution over phase. That's to say, the probability distribution of finding a certain phase is equal to 1 over 2 pi the phase states even though I cannot obtain this probability distribution by doing a projective measurement. There is no projective measurement. There is no Hermitian operator whose probability distribution is this. Because these are not orthogonal projectors. So, one of the things that has been a challenge in quantum metrology, the idea of trying to measure, say, the phase of an oscillator as precise as possible within the confines of quantum mechanics, is how do I design an experiment which gives me this probability distribution? It's a non-trivial thing. Nonetheless, it tells us intrinsically about what the phase uncertainty is. Because that's just related to this probability distribution. This is equal to the mean phase minus the average phase, and I can calculate those things according to this probability distribution. I can do that. Okay. So there's one final thing I want to say with respect to this, which I haven't touched on, I haven't said a word about this semester. Which is the time energy uncertainty principle. We haven't mentioned that. Why not? Well, it's really the same thing as we have over here. I can think about what does it mean to talk about time energy uncertainty. Well, what do I mean by time? Well, in the context of the oscillator, the simple harmonic oscillator, I can think about time as the time over which the particle is oscillating, starting from some origin. And that time is just whatever the phase of the oscillation is divided by omega. So if I had a phase operator, then I have a time operator. In fact, we know that energy is the generator of translations in time. Therefore, we might expect that there's a time operator is the generator of translations in energy. We might expect that. In the same way that we have n is the generator of translations in phase, such that we might expect that phase is the generator of translations in number. But we just showed that mathematically you can't do this because there's a bottom to this. You can't translate below a certain amount. And the same thing is true about there's no time operator. There's no Hermitian operator I can call the time operator because I can't translate an energy below the ground state. There's no mathematical operator that is a Hermitian operator. Nonetheless, we can still talk about, in the same way that we talk about measuring position, number in phase, we can have an energy time uncertainty principle. That's to say, if I look at let me multiply this by h bar omega. I'm just going to multiply both sides by h bar. And then if I say delta n is equal to delta E divided by h bar omega, and delta phi is equal to delta t over omega, for the reasons we just described. Omega delta t, pardon me. Then what I get is delta E delta t is greater than or equal to h bar.
It should be squared, h bar.
It should be squared.
You have
no, it's not. That's not. No, that's correct.
You have delta E over h bar equal greater equal to h bar before, right?
There's an h bar over here that
Oh.
cancels this one.
I didn't see that one.
So, time-energy uncertainty relation is a slippery business. Slippery in the same way as number phase uncertainty is. But it does have a physical meaning. It just means that it doesn't follow from the same kind of measurements of Hermitian observables. There is no measurement I can do with projected outcomes that are time. It just doesn't exist that. But that does not mean that I can't measure time. We do it pretty poorly on this thing, but we measure it in a different kind of way. In the same way that we measure phase, for example, in the interferometer, we can't do it with a Hermitian operator, but we still can measure it, and there are distributions and probabilities, and they satisfy uncertainty principles. All right, we'll conclude there. What we're going to talk about on Thursday, then, is what is the state of the quantum harmonic oscillator that really looks like the classical motion? How do we connect the classical motion of the harmonic oscillator to the quantum states? They're clearly not the energy eigenstates. They have an uncertain phase. We want something whose phase oscillates. There's some superposition, and we'll talk about those next.